Hi, I'm Jeff Cohen from 321 Gang. Welcome to the fourth in our series of videos for systems engineers and software engineers. This video is about modeling requirements. Just to show you where we are and where we're coming from and where we're going to, we've already done several videos on why model, the modeling process and development process, a quick overview of the diagrams, and here we are at modeling requirements. Now, traditionally, people think of modeling requirements as being a systems engineering task. However, it's very important for software engineers too. So even though some of the artifacts that we're going to be talking about are not available in the standard base UML package, in most of the modeling tools, you can include the systems engineering package, the SysML profile, and you'll have these artifacts. Let's start at the beginning. What is a requirement? Or really, what are we going to make assumptions about requirements that we're going to be keeping? Well, first of all, we're going to assume that requirements are going to come from somewhere else. That may be the marketing department if you're doing your own development, or if you're doing a statement of work type project where you're getting requirements from your customer, it would come from there. Traditionally, the systems engineers will look at those requirements, will evaluate them, will refine them, and put them into an archive. And I'm going to assume that you're using some type of requirements repository, something like Doors or Doors NextGen or Gemma or something like that. Even if you're not, at least put them in a spreadsheet or something where you can hold on to them. Because as you'll see, there's a lot more to a requirement than just text. And you really do need to be able to track and trace them. We're also going to assume that when you deliver the requirements, not when you initially receive them, but when you get them and pass them on, they will meet the 5 C's, but initially they don't. And those 5 C's are displayed here: complete, correct, consistent, confirmable, and necessary. Okay, so what are we going to do about all this? We're going to start with the definition of a requirement. And there it is written for you right on the screen. It's a necessary attribute of a system that may be defined as a statement that identifies a capability. You can read this just as well as I can. What's important here is that there's more to the requirement than just the text. It has an identifier, and that identifier is unique throughout the program, and it remains consistent and unique. So if you remove a requirement, happens all the time, you don't reuse that ID. Requirements also include things like the traces and the links from a parent requirement to a child requirement, or from a requirement to the artifact that implements it. These links are very important for a lot of different reasons. The main one is that you maintain a bidirectional trace so that if something changes in a requirement, you know downstream everything that's affected by it. Similarly, if you need to change a test case due to some constraint on hardware or some constraint on the equipment that's available to you, you know everything that's affected upstream of it all the way to the requirement. By the way, this trace also helps you when you're trying to bid or estimate a project too, because over time, if you keep metrics associated with every change and how big it is, you can start doing things like saying, well, if this requirement changes and it affects 3 use cases, 2 classes, 5 tests, and I know, rule of thumb, approximately how much effort it takes to make those changes, you can get a pretty good estimate over time to know how long an individual change will take. By the way, the mechanical and electrical guys have been doing this exact thing for years. They look at a change at how many component diagrams, assembly diagrams, whatever diagrams they have to build, and they base their estimate on that. Requirements can also have constraints. That's a limit on what the requirement can do. So it can set a range or a applicable way that you're going to implement something. That's something especially important if you're getting your statement of work from a customer. Constraint may very well define what makes your solution unique from everybody else's. Requirements also have attributes, for example, tags that may show what build or block it's associated with, It may use other constraints to identify what system and things like that. These attributes help you build a rich tapestry that are the requirements, and this is part of why it helps to be able to have both the rows and the columns. Not to be ignored is the history. We want to know who made changes to the requirement and why. Sometimes this is very important when you're trying to look at why a problem suddenly started occurring, because many times a requirement will be changed for one part of the system, and that may ripple into another part, and that ripple may have been overlooked. Good requirements are very important to outline. So there's certain things which, over time, we say make a good requirement. The first is how you phrase it. In, let's call them traditional requirements, we will generally have a shall statement. A shall indicates that it's required. A will, on the other hand, is something that the system is going to do. It's not a requirement, but it describes a little piece of the system, how it responds to the requirement. Should is something that is advisable. We expect the system should do this. And could is something that's not required, but it is an optional thing that we may want. Now, there are other very common formats that are being used all the time. For example, design thinking and behavioral-based design or development use the if, then, or when an actor does something, the system will respond format, an if, then, else, or a when, else type format. And those are very legitimate requirements that you can track in the exact same way. As I mentioned a couple slides back, the requirements need to meet the 5 C's. They need to be complete. That is, the whole, everything that needs to be done, everything that needs to be understood to implement it correctly needs to be in the requirement. Requirements need to be correct. You can't have 2 different values in the same requirement unless those are really 2 different requirements. Requirements need to be consistent. This is one of my favorite because a lot of times you'll receive statements of work that are boilerplate. In one that I had some years back, the requirement specifically said there won't be or there shall not be any connections from this machine to outside networks. The very next set of requirements was all the requirements for the exterior networks. Now we met with the customer and talked with them and got them to pull those requirements out. Requirements need to be internally consistent and they need to be confirmable. By confirmable, that means testable. So your test guys need to be involved to make sure that they can actually check out and make sure that that requirement can be implemented from their point of view. And of course, the one that doesn't fit in as well is necessary. The requirement needs to be something that you really need to do. This is where we talk about gold plating and things like that that are nice to have, but it isn't a requirement, something that we absolutely have to do. Again, we do need the traces, and we want to have constraints to limit the requirements to be something producible within our realm. When you go to SysML, you have something called a requirements diagram. And a requirements diagram is a way to visualize the requirements, even if they're held somewhere else. These are really good to help you develop requirements and to help you refine them. Notice a few things. The first thing you should notice is the diagram frame. And this headline here that tells you it's a requirements diagram, where it's coming from, where it's held, and of course its name. This is the requirement itself. I've got a stereotype on these requirements so that I can group them together. These are all stakeholder requirements. The requirement has a short name and it's got an identifier and then the text that's associated with it. Now, on many systems, this will work. But on systems where you have thousands or even tens of thousands requirements, if you tried to put all the requirements on one diagram, even if you set them at a number 2 font, and put it on an F-size plotter, you still wouldn't be able to see them all. So while requirements diagrams are really good for looking at things in space and within the specific context that you're using it, don't try to use all of the requirements, but it does make sense to bring them in bring the requirements in and do your traces from there. We've talked about the requirements themselves now. Let's dive in a little deeply inside one of these boxes. So we've already said that in SysML, requirements support the requirement itself and constraints. There's also a third one, and that's a note. A note is something like a sticky note to remind you to do something or to help explain why the requirement is there. It's not necessarily part of the requirement itself, but it is kind of a flavor of or a type of requirement. And notes are very useful when there are some things that aren't really a constraint on the system, but a recommended way of doing something that you want to pass on to the downstream users. UML and SysML support a wide variety of tracing. Now, everything comes from a dependency, and we discussed dependencies before. We'll discuss them later in another part of this series, but a dependency is something that links two artifacts together. Within SysML, we generally see a trace. That's a generic traceability. We also show things like a derived requirement. That is, I'm going to explain or put more information on a requirement, or really I'm going to put more requirements on my subsystems that occurred from the upstream requirements. The generic trace that we use most common is satisfy. Satisfy goes from some model artifact generally that is not a requirement to a requirement. So a use case would satisfy a requirement, or a class or a block would satisfy a requirement. Similarly, verify is used for test cases. So I will trace a test case to a requirement with a verify trace. Refine is a special trace to put more information when we're trying to show how we're going to implement it. And we're going to come to that one later. That's just another page. However, I wanted to hit copy first. Now, copy is allowed. It's part of the SysML. However, there are generally better ways to show copying a requirement than to use the copy. Most tools will support some type of product lifecycle, which will let you control that trace that you want to show, that copying of the requirement for a specific without using the copy. So I recommend to my customers, my clients, don't use the copy. Within SysML and UML, we show the traces with these dependency lines that we're just talking about. These are derived or derived requirement. Notice the arrow goes from the new requirement to the base. That way, this dependency is owned by this child here, and it doesn't have to change the base, the parent element. So those all stay the same, and you can stay within your domain. You can also show requirement traces in a trace matrix, and this is very common. And a matter of fact, for many of the projects that I work with, we have to submit a traceability matrix as part of our deliverables. Even when it's not required by a customer, the groups that I work with that are mature and very effective always build a trace matrix, maintain that trace matrix, and use it regularly. We can also do traces, and this is the satisfy trace, from the use case to the requirement, and this shows you how it's done. Notice again, the direction of the dependency is from the use case to the requirement. So I've shown you traceability, I've talked about it, I keep speaking about it. Let's put it down on paper. Why is bidirectional traceability so important? Well, the first thing is, as you see what elements downstream are affected by that upstream artifact or that upstream requirement. As I said before, it helps with estimates because you can look and see how many artifacts downstream are affected, and with just a little bit of history, keeping just a little bit of history, you'll know. With a group that I worked with that worked on postal systems, we were able to do an estimate in about a year, year and a half. We had some very good orders of magnitude estimates that we were able to do based on this traceability. One of the biggest reasons and one of the most important is to help you quickly find defects when you're doing read clause analysis or read cause defects. If you know what failed and under what conditions it fails. And you can trace that back. You can find the missing piece of a requirement that wasn't seen or the missing part of a constraint that wasn't expected in the system. And you can find those relatively quickly. Most important, though, when you find what's affected, you can find all the other places that might be affected by that same defect. So this keeps it the same effect from propagating into other places in the system. You'll fix it once. It also helps you with your reuse, because if you know how you implemented a requirement earlier, well, you've got all the bits and pieces that you need to implement it again for that specific, for the new specific instance. Now, there are other things that are non-text type requirements. One of them is a use case. Use case is a diagram that's used to group things together, group requirements together in an implementation. We're going to talk about use cases in depth in the next video. You can also use other types of diagrams in addition to text or instead of text to refine that use case, to state what the system is supposed to do. The most common are activity diagrams and state diagrams, because every system that I've worked with has states and modes, and it has flows that go through the systems. We can also use parametric diagrams or timing diagrams. And of course, there's some non-SysML diagrams, non-UML diagrams that we use, things like blueprints or wireframes or wiring diagrams that go along with, and those are requirements as well. This concludes this part of the video series. Our next video is on modeling use cases, and that is going to take all of the requirements themselves, when we have the requirements, and we can group them together into functionality so that we can start building the systems. If you have any questions, feel free to reach out to us at 321-GANG. The address is there. And if you want more information, we'll be happy to give it to you. We also offer consulting and training services. So if you see things that you need, please give us a holler. Thanks.